For this video, we are going to prove these properties with consideration to the properties of transpose, whether these are all true or not. By the way, there is something missing in the first. It's actually equal to A. So we are going to show that the first property holds, as well as for the second, third, and fourth. So the first one is the transpose of A must be this equal to A. By the way, we're going to consider here the given matrices A, B, and C. They are all 2 by 2 matrices. So when you reach later on the second property, which involves multiplication, the third, which involves addition, all the results are actually defined because we have 2 by 2 matrices here. So let's start with the transpose of A, and let's prove it that it's the same, or it will result to A. So first, let us try to come up with this, the transpose of A. The transpose of A is where we are going to change or interchange the entries on the columns and rows of our original A. So it's still 3 and 4 in the main diagonal, and I have here 2, -1. This is the transpose of A. Now, if we are going to transpose this transpose of A, meaning we are going to transpose this as well, it should return to A. So let's see. If we are going to transpose that, 3 and 4 are still here. The 1 will return here, and the 2 will return here. Notice what will happen. This is just the same as our original. This proves that the transpose of A is the matrix A itself, and this holds true. Next property we're going to show is that the transpose of the product of AB is equal to the product of the transpose of B and A in this exact order, because again, there might be some concerns for some results of multiplication if the arrangements are different. So let's start with AB first. Okay, so let's show AB first here. So AB is defined as mentioned earlier. So we are going to multiply the row of A to the columns of B. 3 times 0 is 0. So -1 times 1 is, I have -1 here. The same row for A will be multiplied to the second column of B. So we have 3 times 2 is 6. -1, -4 is +4. 6 and 4, 10. Next, let's focus on the second row of A. 2 and 4 to the same first column of B. 2 times 0 is 0. 4 times 1 is 4. 0 and 4, 4. Next, the same row will be multiplied here in the next column. 2 times 4, 2 rather, is 4. 4 and -4 is -16. 4, -16, I have -12. So if we are going to get the transpose of this product, it will still be -1 here and -12, but the 4 will be placed here and 10 here as well. So this should be the result of the product of the transpose of B and transpose of A, so that the property will hold. Let's try to have the transpose of B first, because we already have the transpose of A here. So we'll be using that later. Transpose of B, considering our given B here. So 0 and -4 is still here, but 1 will be here and 2 will be moved here. So again, the transpose of A is already given in the first. So let's try to multiply transpose of B and then transpose of A. This means that the column of B will be multiplied to the row of B will be multiplied to the column of A. 0 times 3 is 0. 1 times -1 is -1. So probably we're going there. We have the same first entry. Next, the same row will be multiplied to the second column. 0 times 2 is 0. 1 times 4 is 4. Next, the second row of transpose of B will be multiplied to the first column of transpose of A. 2 times 3 is 6. -4, -1 is +4. 6 and 4, 10. And then finally, for the second here and here, 2 times 2 is 4, negative 4 and 4 is negative 16, 4, negative 16, negative 12. See what happens to the two. They just have the same result, and meaning this property holds true as well. So the inverse, or sorry, not the inverse, the transpose of the product of A and B is equal to the product of the transpose B and A in the exact order. Next here, still on transpose, but we are now on addition. So we are going to add first A and B. Sorry. A plus B. So we simply add the entries. 3 and 0 is 3. Negative 1 and 2 is positive 1. 2 and 1, 3. 4, negative 4, 0. When we take the transpose of this, we'll have 3, 0, 3, 0, 1 is here. So this should be the result of this entire operation on your right hand side. Already have the transpose of A here. Already have the transpose of B. So please use that one. So if we have transpose of A plus transpose of B, we will just be adding their entries. 3 plus 0, 3. 2 plus 1, 3. Negative 1 plus 2, 1. 4 plus negative 4, 0. Is this the same as the transpose of the sum of A and B? The answer is yes, and this property holds true for the addition and the transposes. And the last one here is if we are going to take the scalar, the product of the scalar quantity and matrix C before taking its transpose, it should be the same with when we multiply the same scalar to already transpose of C. So let's start with AC first. Our A again is 4. So it's 4 times C. And your C is here. So I'm going to multiply them immediately. 4 times 4, 16. 4 times 1, 4. 4 times negative 3, negative 12. 4 times negative, pardon for that. 4 times negative 2 is negative 8. When we take the transpose of this result, it should be 16, negative 8, 4, negative 12 here. It should be the same with when we multiply the same scalar quantity A, which is 4, to the already transpose of C. So let's start with the transpose of C first. C is here, so its transpose will be 4, still negative 2, negative 3 is here, and 1 is here. When we multiply A, which is 4, to all the entries on the transpose of C, so 4 times 4 is 16, 4 times negative 3 is negative 12, 4 times 1, 4, 4 times negative 2 is negative 8. Notice the two results, they're just the same. Therefore, this property also holds true. So these are the validation of the 4 properties which involve transposes and together with some operations included here. Specifically, multiplication for the second, addition for the first, the third, scalar multiple for the fourth, and for the first is the transpose of the transpose. Thank you for watching.